So we discussed in last class that the acceleration due to gravity g can be given by this formula. So if we consider F to be the gravitational force between Earth and small mass m, then F is given by g times capital M into small m over r squared. Okay, so where capital M is mass of Earth and small m is mass of any object, let's say at some height h, okay, whose distance from the Earth center, it is small r. Okay, then we can substitute F equals to mass times acceleration, and we find this formula for acceleration due to gravity. Okay, this m and m gets cancelled out and we get small g, the acceleration due to gravity, it is gm over r squared. So that means that the acceleration due to gravity, it varies inversely as distance. So as distance increases, the acceleration due to gravity decreases. As distance decreases, the acceleration due to gravity increases. Okay, it varies, it is inversely proportional to r squared. And then we found a formula for acceleration due to gravity at some height h. So we did all these calculations and we found that gh is equal to g times 1 minus twice h over r. Okay, where h is the distance and r is radius of Earth. So gh is acceleration due to gravity at height h, g is the acceleration on Earth's surface. Alright, so this formula is applicable when h is very small compared to r, let's say up to 1%, up to 5% of Earth's radius, not beyond that. Okay, then it will give wrong results if we use this formula when h is comparable to r. Okay, so which one is correct formula? So for all distances, gh over g is equal to r divided by r plus h squared. This is the correct formula, and this formula is an approximation. Okay, and it holds good up to, let's say, 5% when height is 5% of radius of Earth. All right, so this is variation of acceleration due to gravity due to the height. Now we are going to discuss the variation of acceleration due to gravity due to the depth. Okay, so let's suppose we dig a well inside Earth and our object is somewhere over here at depth d below the Earth's surface. So now we want to find out the acceleration due to gravity at this much distance. Okay, so at depth d. So this is the center of Earth, then this is radius r. So we claim that this acceleration due to gravity will be due to this sphere only. Okay, so if we consider radius equal to r minus d, and if we draw a sphere, then the acceleration due to gravity at that distance d, at depth d, will be due to this inner sphere only. Okay, so this is the claim, and how can we justify it? Anyways, so all right, so how can I justify it? So in last class we discussed about acceleration due to gravity or gravitational force due to a spherical shell, and we saw that the gravitational force due to spherical shell inside on an object which is kept inside the spherical shell, it is 0. Okay, so if we consider a spherical shell like this, then if we consider a mass kept inside that spherical shell, then acceleration due to gravity on that mass or gravitational force on that mass due to the spherical shell is equal to 0. Okay, so that means the gravitational acceleration experienced by this mass due to the gravitational force exerted by the shell, it will be equal to 0. Okay, because force is just mass times acceleration. If force is 0, acceleration is 0. So what we can do is we can consider Earth having uniform mass distribution and Earth to be made up of n number of thin shells. So this is suppose the outer shell, this one. Then we can consider another shell inside that, another shell inside that, another shell inside that, up to distance d. And our mass is inside all of these shells. Okay, so our mass is here, so that means it is inside all of these other shells, and therefore the gravitational force due to these outer shells on this mass, it is equal to 0. Okay, and therefore the gravitational um, acceleration or acceleration due to gravity due to outer part of Earth will be 0. Okay, and what we can say is it will experience the acceleration due to gravity only due to this inner shell. So is this point clear? Yes, Naresh? All right. So now let's do what we have just explained. So let's consider the density of Earth. So let's suppose that the Earth has uniform mass distribution. So Earth, this is an assumption. Okay, so assumption is Earth has uniform mass distribution, and therefore density of Earth rho can be given by m equals to rho equals to mass divided by volume. Okay, and what is volume of a sphere? It is 4 by 3 pi r cube. All right, so m divided by 4 by 3 pi r cube, and therefore I can write mass m is equal to rho multiplied by 4 by 3 pi r cube. So I will just write it as 4 by 3 times rho into pi r cube. Okay, so this is mass of Earth. Okay, so let's call this equation number 1. Then what is acceleration due to gravity due to Earth? So acceleration due to gravity on Earth's surface has a formula g equals to gm over r squared. Okay, and now what I will do is I will substitute this m from equation 1, which is 4 by 3 rho multiplied by pi r cube. All right, so this can be written as g over r raised to 2 multiplied by 4 by 3 pi rho into pi r cube, or pi into rho into r cube. Okay, and now we can see that this r raised to 3 gets cancelled out with r raised to 2, that is r cube upon r squared gives us r, and we can write g equals to 4 by 3. Okay, it is pi r rho and capital G. All right, so let's call this equation 2. Okay, so after that, let's consider the acceleration due to gravity due to this reduced mass. Okay, so that inner sphere, and I will say that acceleration due to gravity at depth d, at depth d is just due to a sphere of radius r minus d, okay, which is centered at, whose center is at center of earth. Okay, so now therefore acceleration due to gravity at depth d, this suffix d is for depth d, it will be equal to, so if we just compare it with this formula, what are the changes um, in this formula and the formula that we want to write? Okay, so what are the changes in the acceleration due to gravity on earth's surface and at depth d? So if we look at this formula, 4 by 3 is constant, pi is constant, r changes. Okay, here it's r, and acceleration due to gravity at depth d will be due to what? A sphere of radius r minus d. On earth's surface, the acceleration is due to the sphere of radius capital R. Okay, then rho, we considered earth having uniform mass distribution, so rho will remain constant, it is density of earth, and g is a constant. So only one thing changes, and therefore we can write down this formula for acceleration due to gravity at depth d very easily. It will be 4 by 3, pi will remain as it is, this r minus d multiplied by rho g. Okay, and I will call this equation number 3. So is this thing clear? Okay, so I had doubt, when a person is on earth, its weight is 12, then what will be weight of person on moon when g is 1 by 8 times of earth? Okay, we can discuss it afterwards. Okay, so all right, so what I'm saying is we found this formula for acceleration due to gravity due to earth. Okay, so earth is a sphere having radius r. So this is this is acceleration due to gravity due to what? A sphere having radius r. All right, on earth's surface. Okay, so this formula is 4 by 3 pi r rho g, and acceleration due to gravity inside the earth's surface at depth d, we argued that it will be due to this inner sphere only. Okay, and this part, the outer part of earth, it will not play any role, it will not exert any gravitational force on an object which is inside the earth's surface. Okay, so the acceleration due to gravity will be due to this inner sphere of radius r minus d. And if we compare, so if we want to write formula for it, then acceleration due to gravity due to a sphere having radius r, it is equal to 4 by 3 pi r rho g. So 4 by 3 pi is a constant, rho and g, they are constant. Okay, because we considered that earth has uniform mass distribution, and therefore we can easily write down the formula for acceleration due to gravity at depth d, which will be due to a sphere having density equal to density of earth and whose radius is equal to what? R minus d. So we just have to change this r, we just have to replace this r with different radius r minus d. Okay. Okay, that is good question, Naresh. The density of earth and inner sphere, it cannot be same. All right, so this is an approximation again. All right. Okay, so now what I will do is I will just divide equation 3 by equation 2. So let's just add a page. There is a problem. Okay, so I will divide equation 3 by equation 2. What do we get? So g at depth d divided by g at depth d divided by g will be equal to, equation 3 is 4 by 3 pi r minus d rho capital G divided by just 4 by 3 pi r rho g. Okay, and look here, this 4 by 3 pi and 4 by 3 pi gets cancelled out, rho and rho gets cancelled out, g and g gets cancelled out, and we get this simple formula. It is r minus d divided by r. This is g at depth d divided by g on earth surface. So we'll take g on other side and we will divide by this r. So r divided by r is 1. So we can write g at depth d is equal to g on earth surface multiplied by 1 minus d by r. Okay. So this is the acceleration due to gravity at depth d below the earth surface. And so considering this previous approximation that earth's density is constant throughout, which is not, so if we just neglect that fact, then this formula holds good for any depth. Okay, so is it clear? Yes. What is formula for g? G is actually, on earth surface we consider its value to be 9.8, around 9.8 meter per second squared, and formula for g is gm or r squared. Okay, this we studied in last class. And in terms of the radius of earth, sorry, in terms of density of earth, the formula for g is 4 by 3 pi r rho g. Okay, Is that clear, Geeta? Main formula in which you have substituted. Sorry, I didn't get that. Main formula in which you have substituted. Okay, it is this formula. See, I considered the density of Earth is its mass upon volume. So m divided by 4 by 3 pi r cube. So mass can be written as this. Okay, 4 by 3 density times pi r cube. And I had substituted that in this formula. G equals to gm over r squared. So if we substitute this mass 4 by 3 pi r cube multiplied by rho in this formula, then you get this formula. Okay, and we have used this formula to find out the acceleration due to gravity at depth d. Hope it is clear now. Okay, good. So after that, we'll discuss another variation in g, that is variation in g due to the altitude. Okay, so let's draw a sphere again. Yes, Naresh, notes will be available on Google Classroom after we end this chapter. Okay, so let's draw a sphere again. So this is our Earth, and we know that Earth rotates about itself. Okay, the period of rotation is 24 hours, and due to that rotation we have days and nights. All right, so let's suppose this is an axis about which the Earth rotates from west to east. So here it has to be clockwise sense, sorry, anti-clockwise sense. Anyways, after that I will draw an equator of Earth. So this is an equator. This is center of Earth O. And let's suppose that we have an object somewhere over here. Okay. So as Earth rotates, every object on Earth's surface, it moves in a circle. So this object will move in this circle, and we saw that circular motion is an accelerated motion. Okay, so every object which is in accelerated frame of reference, that is in non-inertial frame of reference, experiences a pseudo force, and here the pseudo force will be the centrifugal force. Okay, so how much will be the centrifugal force? So if Earth rotates with angular velocity omega, then the pseudo force experienced by any object, and let's draw its radius. So its radius is, let's say, small r. Okay, by this object of mass m, revolving in a circle of radius r. So that pseudo force is given by what? Let's write it as F suffix P. It's equal to m r omega squared. Okay, and it is revolving with angular speed omega. Okay. Okay, Geeta is saying what is pseudo force? Okay, so pseudo force is like um, okay, so let's suppose you are standing in a bus and bus accelerates suddenly. Okay, so bus is at rest and it starts. So you get a backward jerk. All right. So you feel as if there is some force acting on you in backwards direction. So you will be like falling backwards. Okay. So you cannot explain the origin of that force, but you feel that force because you are in accelerated frame of reference, okay, where Newton's laws are not applicable. Okay, so that force whose origin cannot be explained, but which you have to take into consideration to apply the Newton's laws in the accelerated frame of reference, it is known as pseudo force. All right, so it is experienced by a person who is in accelerated frame of reference and the force is opposite to that of the acceleration. Okay, so if you want to learn more about this, then you can watch my lectures on laws of motion. All right, so there I have explained it in detail. So summary is this one. Okay, so now this force, the pseudo force, it will act in this direction and an object over here, let's say a person over here, will feel an acceleration in this direction. Okay, whose magnitude will be what? This force divided by mass. It is r times omega squared. All right. So that acceleration, let's call it a suffix p because it is due to the pseudo force. Okay. Then now, okay, so I will draw a line from center of the earth joining this point. So this much distance is r. Okay, it is radius of earth only, and the altitude can be given by this angle phi. Okay, the position of this object with respect to what? With respect to the center of earth, it can be given by this radius, and okay, there will be longitudes and latitudes, but we can say that position will be somewhere on the angle phi. Okay, with respect to what? With respect to the equatorial plane. Okay, the phi is the angle made by its radius vector with respect to the equatorial plane. All right, is this clear? Yes, no? Okay, then now what is relation between small r and capital R? So if this angle is phi, then this one will be 90 minus phi, and again I can say that this angle over here is phi. So if you see this triangle, then I can say that cos phi will be small r divided by capital R. So which implies that small r equals to r times cosine of phi. Okay. After that, now let's consider the central forces, sorry, force due to the the gravitational force, and the component of this force, pseudo force, acting in this direction, the radial direction. So let's consider those forces. So now we know that acceleration due to gravity acts along this line, and its value will be g. Okay, so now if we take this acceleration, which is due to the pseudo force, and if we resolve it in two perpendicular components, then if I extend this line, so if this angle is phi, this angle will also be phi. Okay, it's vertically opposite angle, and therefore the component of AP in this direction will be AP cosine phi. Okay, and we don't want perpendicular component, but it will be AP sine phi. All right, this component will be AP sine phi. Okay, then now what are the how much is the acceleration, net acceleration acting on that object towards the center of earth, because that will be the resultant acceleration due to gravity. So net acceleration on mass m towards the center of earth, and I will call it g suffix phi, it will be equal to g, which is normal acceleration due to gravity experienced by an object on earth's surface. So this is acceleration due to gravity, whose value can be given by gm over r squared, which we have studied before. Okay, so this formula we have studied before, minus this component of acceleration due to the pseudo force experienced by this object. Okay, so it is AP cosine phi. All right, so it is AP cos phi. And how much is magnitude of AP? So magnitude of AP can be found from this formula. So now FP can be written as, so I will write it here. So FP can be written as M times AP, and this gives us AP A suffix P equals to R omega squared. Okay, and if we use this value R equals to capital R cosine phi, then okay, let's write it, let's call this equation 1, this one equation 2, this one equation 3. So okay, Naresh is saying will they be equal? Will what be equal, Naresh? Yes. No, no, no. AP cosine phi and G will not be equal. Okay. It is AP cosine phi is, it's very small. Okay, it's of the order of 0.1, it depends, but of the order of 0.1 meter per second squared. All right, at max. So, and we can calculate that, I will tell you. So, G at altitude phi is equal to G minus this AP. AP is r omega squared, small r into omega squared cos phi, and small r can be written as capital R times cos phi using this equation 3. So we can write this as G minus r cos phi into omega square cos phi, or we can just multiply out this cos phi and cos phi, which becomes cos square phi. So we have G minus r omega squared cos square of phi. So this is formula for acceleration due to gravity at altitude phi. Okay. So where will this formula be maximum? Sorry, where this acceleration due to gravity will be maximum and where will it be minimum? So of course, for acceleration due to gravity to be maximum, this factor should be minimum, and that means if cosine phi is equal to 0, okay, then this factor will be equal to 0, that is minimum. Okay, so we know cos 0 is 1, cos 90 is 0, and that means, so we know cosine of 90 degrees is 0, and that means at poles where the altitude is 90 degrees, okay, this angle phi is 90 degrees, so at poles g phi will be equal to g. Okay, so I can say at poles phi equals to 90 degrees, and therefore cosine phi equals to 0, and therefore we have g at poles. Let me write at poles only. North pole and south pole, it is just equal to g, okay, which is equal to gm over r squared. And at equator there is maximum change in acceleration due to gravity, so phi is equal to 0, and therefore cosine of phi is equal to 1. So the centrifugal force experienced by an object on the equator, it's maximum, and it brings out maximum change in acceleration due to gravity. So therefore we have g at equator equals to g, which is gm over r squared divided by, sorry, minus r into omega squared. Okay. Okay, is this thing clear? Yes, is it clear? Here we are talking about poles. So this uh, this formula is for poles and this one is for equator. So we are just Okay, we just need to know the angle made by radius vector with equatorial plane. Nothing else. All right. So now, and uh, that's what we are using to define an altitude. Okay. All right. So then now if you want to find out how much will be the change in acceleration due to gravity, so due to the altitude, what you can do is you can find out this factor, this factor r omega squared. So r is radius of earth, whose value is about 6400 kilometers, I guess. Okay. And omega is the rotational speed of earth, angular velocity you can say, or angular speed. So it is 2 pi divided by time period of earth's rotation, which is 24 hours. So put 24 hours over here, convert it into what? Seconds, then convert this into meters per second, meters, and if you substitute all of that, you will get a value of r omega squared. Okay, which will be something around zero point 0.1 or something. So its order of magnitude will be zero point 0.1 meters per second squared. All right. So we can say the acceleration due to gravity is minimum at the equator and it is maximum at poles. Can we take it at an instant using instantaneous formula? No, I couldn't get this, Naresh. What what do you mean by this? Instantaneous formula for omega. So for Earth, how will you define the instantaneous formula? We only know that time period is 24 hours. So to find omega, we have to use this formula only, 2 pi divided by capital T. The angle made by rotation. Okay. Yeah, you can, okay, in principle, you can do that. So you can find out, let's say in 6 hours, the earth will rotate by 90 degrees, in 3 hours by 45 degrees or so. Am I correct? Yes. So then how much time is elapsed, and you can substitute that, but we don't need to do that, right? All right. So now we have discussed variation in acceleration due to gravity uh, with respect to due to the height, due to depth, and due to altitude. Okay, there is another fact that Earth is not a uniform sphere. Okay, so there are hills and dales like Mount Everest. Okay, there are hills like Mount Everest and valleys of equal size. Okay, not equal, but let's say of comparable sizes. So Earth is not a uniform sphere, and that's why the acceleration due to gravity everywhere on Earth, it won't be same. Okay, or this formula, every formula that we are talking about, it is an approximate formula because Earth is not a uniform sphere. Okay, and there is another fact that the radius of Earth, it is not constant. At poles it is different. So Earth is like this ellipsoid. Okay, so it is bulged at equator and it is flattened at the poles. So this R, if we call this R, then this will be R plus some value, let's say X. Okay. So difference between radius at equator and radius at poles, it is about some 20 something kilometers. Okay. But that is small compared to the radius of Earth, which is 6,400 kilometers. And that's why we are neglecting those things. Or we can neglect those things, the shape and size of Earth, and we can do a nice approximation, and we can have all these nice formulae. All right. So now if there is no more questions on acceleration due to gravity, we'll move on to the gravitational potential energy. Okay. So now, okay, where can we define potential energy? So what is the condition to define potential energy? The condition is forces involved must be conservative forces, and the gravitational force is a conservative force. So how do we know that? The work done against the gravitational force does not depend on path followed. Okay. So now let's consider an object. Okay, so I will consider, let's say, this object having mass capital M. Okay, why? Because we can always call it mass of Earth, and we can use general formula that we are going to derive for special case of Earth. Okay, so there is another mass, let's say small m, which is somewhere at infinity, and we are bringing it from there and we are keeping it over here at some distance. Okay, let's say R. Okay, I will join this line first. Okay, so I have to erase this mass. So mass is suppose here, and that initial distance is infinity, and I bring it and I keep it over here. So let's suppose this much distance is R, and this is some intermediate distance. So I'm bringing that mass from very far away, the distance which I cannot measure, that is from infinity. So while bringing it, there will be some intermediate distance, let's call it x. Okay. So then now what we are trying to do is we'll bring mass small m from infinity okay, and we want to keep it at distance r away from another mass capital M. Okay, so this mass small m, it will experience some gravitational force. Okay, so gravitational force experienced by this mass. So let's say at distance x, f suffix g, let's call it f, okay, f suffix g equals to what? gmm over x squared, okay. And if I want to consider the direction also, then what will be the direction? So gravitational force is an attractive force. So if we consider this mass capital M to be at origin and we start measuring distances from there, then it will be directed along minus x, okay. So this negative sign. So negative sign means the force is attractive. All right. What is x? So what I am doing is I am bringing a mass small x from infinity, okay, and I want to put it at distance r from mass capital M, but in between there is some distance, okay, it can be anything. So in between from infinity to r there is some intermediate distance, I am calling it x, okay. So now I can say work done to displace this object, to displace this mass small m by dx, okay. So let's suppose dx is positive and this work done is against gravity, okay. So I can say, or let me write it explicitly, it is against gravity. So work done, I will write it here, against gravity, okay. So it is dw, it is equal to what? Minus of the gravitational force, we are calling it f suffix g, times dx, okay. So that is, if we substitute gravitational force, then it is minus gmm or x squared. So that minus and minus, those. So can you upload regular class 12 videos? Yeah. Okay, Diban. Actually, I am conducting class 11 right now, and I will start uploading. Not uploading. I will start conducting class 12 on something around March. In which class you are, Diban? Yeah. Okay. So then the gravitational force is minus gmm or x squared. So if we substitute that, we get gmm or x squared times dx, okay. And therefore work done to move it from some initial distance r1 to final distance r2. So work done for displacement from r1 to r2, it is integral from r1 to r2 of dw, okay. And what is dw? It is gmm over x squared dx. So GMM is constant, we can take it outside. So this is equal to integral from R1 to R2. Oh, I'm sorry, I wanted to take GMM outside. So G capital M small m I'm taking outside. So integral from R1 to R2 of 1 upon x square dx, or this can be written as x raised to minus 2 dx. Okay. I'm sorry. Okay, then this can be written as w equals to g capital M into small m. Now what will be this integral? Integral of x raised to minus 2 dx. So we know this formula, integral of x raised to n dx from some initial, let's say x1 to x2, it's equal to what? X raised to n plus 1 divided by n plus 1. Okay, lower limit is x1, upper limit is x2. So if we substitute, and this formula is valid when n is not equal to minus 1. Okay, so in that case integral will be log. Anyways, so now n is minus 2, so x raised to minus 2 plus 1 is minus 1. So this integral will be x raised to minus 1 divided by minus 1, or we can say it is minus 1 divided by x. Okay, this minus 1 we can take it in numerator. So this can be written as g times m into m minus 1, and x raised to minus 1 can be written as 1 over x. So from R1 to R2. Okay. So is it clear? Okay. Actually, I cannot explain that in detail. Just derivative of log x, okay, is 1 over x. Okay. So integral of 1 over x will be log x. All right. 1 over x can be written as what? X raised to minus 1. So integral of x raised to minus 1 will be log x. Okay, so this is special case, and for any other value of n we can use this formula. So integral of x raised to n dx is x raised to n plus 1 divided by n plus 1. All right. So now let's substitute R2 and R1. So we get work done equals to what? GMM GMM multiplied by this thing. If we substitute the upper limit, it's minus 1 over R2, and then minus we have 1 over minus 1 over R1. Okay. So, or we can take minus sign outside. Okay, let's take minus sign outside. So it's 1 by x only. So it will be 1 by the upper limit, 1 divided by upper limit, 1 upon R2 minus 1 upon R1. All right. If you take negative sign outside. Clear till this point? It will be positive. What will be positive? Oh, I am taking negative sign outside, then no, 1 by x will remain. So 1 by r2 minus 1 by r1. That's correct. Inside those brackets. Over here, no, it is, see, mm, whatever integral you have to substitute the upper limit and lower limit in that integral. Okay. So if you substitute upper limit, it's 1 by r2, lower limit, you will get 1 by r1. Okay. So then let's consider the initial position. Let's suppose that r1 is equal to infinity and r2 is equal to distance r. Okay, so we are moving that object from infinity to r. So is this thing clear? So if we substitute that, r1 is infinity, so 1 by r1 is 1 divided by infinity, so that will become 0. Okay, and therefore we get minus of g capital M into small m or r2. R2 is what? R. So this much is work done against the gravitational force, okay, to bring an object from infinity to distance r. All right. So let me check whether this sign is correct. You give me 1 minute. Okay. So I hope my calculations are correct and the sign is correct. Okay. So then we know that work done against the gravitational force, work done against the conservative force, it gets stored as potential energy of the system. Okay. And therefore I can say that potential energy of mass m or the system, let's write it as, okay, let's write potential energy by letter u, it's equal to minus of g capital M into small m over r. Okay. So this is potential energy of system of two masses brought from infinity. Okay. So is it clear? Will energy be negative? Yeah, potential energy can be negative. Okay. Then, okay, now let's consider let's talk about an escape speed. Okay, so let's suppose we throw an object from Earth's surface. It goes to some distance and it falls back. Okay, so if this is our Earth and we throw an object, let's say stone, then it goes to some distance and it falls back. So why does it come back? It's because uh, of what? Earth pulls it back. Okay, due to the gravitational force, it accelerates downwards. Okay, so acceleration is negative throughout its motion. So now the let's suppose we have any mass on Earth's surface. So let's suppose we have a projectile, or let's say a rocket over here, and we want to send this rocket to infinity. Okay, so we want to send this rocket till infinity. So with what speed we should send this rocket, we should throw this rocket, okay, or what initial velocity should we impart to this rocket so that it goes to infinity and never comes back. So that speed is known as the escape speed, the speed which we must impart to an object such that it escapes from Earth's gravitational bounds and it goes to infinity. It is known as the escape speed. Okay. So now we can use law of conservation of energy and we can find out that speed. So we can say that sum of potential energy and kinetic energy remains constant. So okay, let me just write down what is the escape speed. The speed it's the speed with which if object is thrown from Earth's surface, it escapes out of Earth's gravitational bounds to infinity and never comes back. Okay, so now we can say the potential energy U plus K on Earth's surface is equal to U plus K at infinity. So U at infinity is already 0. Okay, so U on Earth's surface is U at distance r plus is is the kinetic energy that we are giving to that object, so which is half of mass of the object multiplied by v squared, but we want to find out the escape speed, so it is v suffix e squared. Okay, where ve is the escape speed, the speed which we will give to the object and object will escape out to infinity. Object will escape out of Earth's gravitational bound and it will reach infinity. So u at infinity plus k at infinity. Okay, so now we know that u at infinity, okay, we consider it to be 0. Okay, so the formula will be gmm divided by r. So what we do is we consider that the gravitational potential energy of object at infinity is 0, because uh, in gravitational potential energy what we consider is the formula is gmm divided by r. So how do we define gravitational potential energy? We define it like work done to bring an object from infinity to some distance. Okay, so we consider potential energy at infinity is 0, and then we get simple formula for this gravitational potential energy at distance r as minus gmm or r. And if we substitute in this formula r equals to infinity, again we get u at infinity equals to 0. Okay, so we are defining it in that way, that gravitational potential energy at infinity is 0, and we are calculating all potential energies with respect to that potential energy. Okay, so just like we did for the spring. Is this point clear? Yes. Radius and work done are inverse. It's not radius, it is distance between two objects. Okay, and it's not radius, it is distance between two objects. So if you are bringing an object from infinity, then yes, you can say that work done is inversely proportional to the final distance. Okay, all right. So what is potential energy at infinity? It's 0, and we don't mind if object goes to infinity, that is this rocket goes to infinity and stops there. Okay, so what we'll do is we'll write potential energy at infinity is 0 and kinetic energy at infinity is 0. It is half of mv at infinity square, and we'll say that object goes to infinity and stops there. So v at infinity is 0. Okay, even if it stops there, it will not come back. Okay, because the gravitational force it experiences, it will be negligible. Actually, if it is at actual infinity, then gravitational force will be 0. Okay, because it is gmm or r squared. So if you keep r equals to infinity, then gmm or r squared will be 0. Okay, so no acceleration. Then now let's substitute. So right hand side is 0, so this is 0. So u of r is minus of gmm over capital R, because if earth is this object is on earth's surface, the distance between that object and center of the earth, it is what? Capital R. Okay, so that much is the gravitational potential energy of an object on earth's surface, plus half of m into v squared. Then you can cancel out m, small m if you like, and you can simplify this, so you get half of v squared equals to gm over r. You can take 2 on other side, so v squared will be 2 times gm over capital R, and if you want v, then it will be square root of that. Okay, so this is the escape speed. All right, and then you can use this formula, g equals to gm over r squared, which will give you gm equals to gr squared, and you can substitute that over here. Okay, so you get v suffix e equals to square root of 2 times gr squared divided by r. So this square will get cancelled out with r, and you get this another formula, alternate formula, square root of 2g capital R. Okay, so This is the velocity with which you should throw an object such that it escapes Earth's gravitational bounds. So you can substitute g, which is 9.8 meters per second squared, r equals to what? 6,400 kilometers, and you can find out the escape velocity. Okay, I don't remember the value right now, but this is how we can find it out. Is this thing clear? Okay, so now we'll stop at this point. Okay, and we will discuss about satellites in next class. All right then, good day. Yes, welcome.